Hello, this is Dr. Smith, and in this video I'm going to talk about some of the topics related to relational algebra. This video is intended for students who are in a database course and may be asked to read a little bit on relational algebra. Recall that in a data model, you describe the structure of a database and you describe behavior of the database application. Relational algebra is the component of the relational data model that describes the data behavior of the retrieval requests from the database application. So in the past, you may have studied the relational model that describes the data in a relational database. In addition to the data model, we can talk about the data request. How are we going to model the data request? Likewise, how are we going to model the result of the request for data? When you studied the relational data model, you probably were introduced to graphics that are similar to the one before you. In this case, we use a picture of the data to represent what the data would look like within the relational data model. So, for example, EMP can be described as a table. This table is sometimes characterized by column headings, also known as attributes, and the instances of the data listed below the column heading. So this is a picture of a data model. This is sometimes called the logical view of the data model. But perhaps we can introduce a slightly different way of looking at this model. Instead of looking at it as a table with column headings and instances of the data, let's suppose I tell you that this graphic really represents what is known as a set of data. So, EMP is the name of a set. The set contains only elements. There are no column headings in a set. If you remember, a set is just a group of items. And somehow or other, we want to denote the fact that the elements of the set consist of an entry of data that you might describe as corresponding to a row. To do that, we say that this set consists of tuples. In this sense, then, each tuple has 3 elements. And we consider a tuple an ordered list so that the first element corresponds to an employee number, the second element the employee name, and the third element, in this case, the title of the employee. With that in mind, the column headings, even though they're not part of the set, they represent the possible values of the components of the tuple element. So employee number, this ENO, would represent what is known as the domain of the employee number. You know, what does the value of an employee number look like? When we talk about a set of data within the relational model, we call that set of data a relation. So we say that EMP is a relation, and in this example, it is a set with 8 members. Now I wanted to introduce an operator. An operator is something that does something on a set. I don't want to go into the definition of mathematical operators, but it goes like this. The operator I wanted to talk about is this operator that has this symbol of an X. Sometimes it's called a product, sometimes it's called a cross product. And very simply, what this product or cross product refers to is that it's going to look like, in this notation that I'm using, I am going to consider ENO, which I said was the domain of the employee number, as a listing of the possible values that the employee number can take on. That's one way of defining the domain. Maybe we can say that the employee number can only take on values E1 through E8. And if I take the cross product of employee number with name, or the employee's name, where if we were to say the domain of the employee name refers to only those possible values of the employee names, then the cross product will then take starting with, let's say, the first value of employee number, and then it will create a new set that consists of the first element, then the second element. Now, the first element is from ENO, the second element is from EN name, and because I'm crossing it with title, the third element is electrical engineer. And then I repeat the first element and I cross it, let's say, with the second element of employee name. Here it is, over here. I'm doing it out of order of my example. And I cross it with electrical engineer. So the idea is that we just want all combinations of employee name, employee number, and title. So if I continued this list, I would have all combinations. So if I have 8 employee numbers, 8 employee names, and 4 different titles, 8 times 8 times 4 would be the number of elements in this new set. So an operator just takes things out of one set or 2 sets, and in this case, because we consider the cross product a binary operator. It does something in conjunction with 2 sets. We take that result and then we're going to cross it with the set title. Well, in any event, by doing so, we can say that this set does not represent the employee data set. What this is just a way of illustrating that the employee set of data is a subset of the set of data created when we cross all these possible values. Why am I talking about this? Well, I just find that it's an operator that many students may not be familiar with when they talk about set operations. Just as an aside, the most common set operations you know about it are things like adding, subtracting, or let's just say adding and multiplication, where you add 2 numbers and two real numbers, the result is a number in the real set of numbers. Here, when we have an operator, in this case, our result is not within the set of that we operated on. We created a new set. That's a little bit of, I don't even remember where I learned that. Okay, so when we talk about relational algebra, which is a way to formulate a data request where the data is represented in a relational data model, This was done by E.F. Codd in 1972, and he defined the set operations on a relational database, and they're listed here. And I'm only going to briefly talk about select, project, and product. Now, product will look familiar since we already talked about it. So, when we talk about select, we always want to think about selecting tuples from a relation. And formally, the tuples that are requested from a relation oftentimes are restricted, and that restriction is described by a condition, or it is also sometimes referred to as a selection predicate. So if we have EMP, which is a relation, a set of data, and we also know that it has an attribute, or the first tuple, or the first element of the tuples are restricted by the domain described by ENO, that we can create an expression here that tells us what tuple we are requesting from the relation. So the construction of this notation is not too hard. We read this as select from the relation EMP, subject to the condition that we want to select the tuple where the value of the employee number is equal to E1. And if we express that in set notation or mathematical notation or a combination of both, we see that this expression is equal to, or results in, a set. We indicate that with braces. And we're suggesting that we are taking an element out of that relation. Remember, the element of that relation is called a tuple. We're taking elements, any element that satisfies, or as we read this horizontal line, such that, all tuples such that the tuple whose element ENO is equal to E1. That is the selection. So we select all tuples such that the value of ENO is equal to E1. And as we know, there was only one tuple with employee number 1, and I express it here. Another operation on a relation is called a projection. So we project on a relation using this notation. This is called a pi. By the way, in that previous slide, this is a sigma. Whoop. So a projection always extracts specified attributes from a relation. Attributes meaning that column that we referred to earlier in the tabular representation of our relation. So in any event, we let EMP be a relation that contains an attribute ENO, employee number. So we want to project from the employee relation. Notice how we put the relation name inside the parentheses. This operator is on the outside. And here's our restriction, ENO. And what we're doing is we're selecting the column or attribute ENO from the employee relation. And if we express it in this notation, this says we're going to extract all tuples of ENO, tuples with all tuples that are returned have a column ENO. such that T is belong to EMP. Okay, so we have a tuple that's a member of EMP, and so we have 8 tuples that are members of EMP. So for each tuple, we return the employee number, ENO. And we see that we can list that in this way. Well, I hope I didn't confuse you too much on that one. The last operation is called product, as I mentioned earlier. And very often we use a product to extract data from 2 tables. In my earlier introduction, I showed how you can denote the cross product of 2 sets that were represented by domains of the 2 attributes. So here, we see that for every employee that was represented in the employee data set, I don't know if you remember, there were 8 of them. Here's the first one, here's the second one. We're going to append to that tuple that was referred to in the employee relation, the tuple, each tuple that's found in the pay relation. So evidently we only had 4 different tuples in our pay relation. Whoops. Let's go back. Where is it? Here it is. 1, 2, 3, 4. Pay. We only had 4 entries in here. So we're going to cross EMP with pay. So for the first tuple, we are going to append it 4 times, once with each possible tuple in the pay relation. And that's what we show here. So if you've never seen some of this material before, it may look really strange, so I think it's worth having a little brief introduction. Thank you.